I'm Gerhard Neumann, so I will be chairing session number 5, the reinforcement learning session, where we'll look at various aspects of robot reinforcement learning. So we have 4 very interesting papers with a special focus on offline reinforcement learning. So the first paper is from Wenxian Zhu from CMU, which is about latent action space for offline reinforcement learning. So Wenxian, do you want to share your screen?
Okay. Can you see my screen?
Yes, that works. So okay. Yeah, please go ahead. And if there are questions, please post them in the Q&A.
Okay. Hi, everyone. I'm Wenxian from the Robotics Institute at CMU. I'm going to talk about our work on latent action space for offline reinforcement learning. This is joint work with Sujay Bajracharya and Professor David Held. In this work, we propose a simple and effective offline RL method. It learns the policy in the latent action space to avoid out-of-distribution actions. It achieves competitive performance on both simulated and real robot experiments. The motivation behind our work starts from this question. Deep reinforcement learning has been a powerful tool for decision-making problems. So what is prohibiting us from training deep RL on real robots? One of the reasons is that data collection in robotics is especially expensive and potentially dangerous, but reinforcement learning requires a lot of interactive data. There's an even more frustrating problem. So current algorithms are mainly based on the pipeline that repeatedly collects data and updates the policy. It usually requires interactive data that is generated by the current policy. This means for each new experiment, we throw everything away and then collect data from scratch. In contrast, offline reinforcement learning studies the problem of learning a policy from a static data set of transitions without further data collection. This paradigm will be especially important for robotics. Static data sets allow more flexibility in data collection, so we can include human demonstrations, reuse the rollouts from previous experiments, and also, more importantly, to share the data sets within the community. In this way, the data set will be more likely to be scaled up in size. And a more effective use of data can allow us to see more reinforcement learning experiments on real robots. Although off-policy algorithms use a buffer to save the rollouts, popular Q-learning-based off-policy algorithms, such as DDPG or TD3, cannot be directly used for the offline RL problems. This is because of the out-of-distribution actions. In Bellman update, the Q value at time t depends on the Q value at the next date following the current policy. The policy might select action that is not included in the static data set. This kind of out-of-distribution actions will lead to extrapolation error of the Q value. And this error will then be accumulated by the Bellman operator and exacerbated by the policy updates. It eventually leads to overestimation bias that hurts the performance. So intuitively, it means the policy might select some action that has a high Q value, but this Q value is actually wrong because it is not in the data set. This overestimation bias has always been an issue for Q-learning-based methods, but this is especially problematic when we're using a static data set and when the action space is large, such as continuous action space with high dimension. To avoid extrapolation error, we need to constrain the policy to select actions within the support of the data set. And the data set is usually modeled as a behavior policy, and we call it pi-b. As illustrated in this figure, we can only select actions under the green region when pi-b is larger than a threshold epsilon. On the other hand, the constraint cannot be overly restrictive. The policy should not be affected by the density of pi-b. In this example, the policy should have the flexibility to choose any action within the green region, even it deviates from the most probable action of pi-b, and the shape of the distribution looks very different. Previous methods struggled with these two objectives. For example, BCQ proposes to sample from the behavior policy, perturb around it, and then take an action that maximizes the Q value. This method will be restricted by the density of the behavior policy distribution if the sample size n is not large enough. Another line of work uses explicit policy constraint in the optimization process. They try to force the agent policy to be close to the behavior policy in terms of different measures of distance, such as KL divergence or MMD. However, in some cases, for example, in Bear, the constraint might not be easily satisfied during the optimization. Another challenge of using the explicit constraint is that the choice of distance measures such as KL divergence will make the policy be restricted by the density of pi b. We aim to propose a method that can satisfy both of these two objectives. In our method, we first model the behavior policy using a conditional variational autoencoder, as in previous work. It is trained to reconstruct actions conditioned on states. The decoder creates a mapping from the latent space to the action space. So instead of training a policy in the action space of the environment, we propose to train a policy in the latent action space of this VAE, and then use the pre-trained decoder
Wenxian, are you still there?
Can you hear me?
Yes, we can hear you.
Okay.
Okay, please continue.
So let's go back to our objectives. We can naturally constrain the policy to select actions within the dataset because the action is chosen from the latent space. To zoom in a little bit, the prior of the latent variable of VAE is usually set to be a normal distribution. To avoid the latent policy from selecting actions that are far away from this prior, we use a 10H at the output of the policy. It is only allowed to select within 1 or 2 standard deviation of the Gaussian. We also satisfy the second objective because the policy can select any action within the latent space and will not be affected by the density of the behavior policy. We evaluate our algorithm on a wide range of continuous control tasks, including a real robot experiment and the D4L benchmarks. The task for the real robot experiment is to slide along the edge of the cloth as fast as possible without dropping it. It has a tactile sensor attached at the fingertip. The standard dataset we use is composed of a replay buffer from a previous experiment and 5 episodes of expert rollouts. Here's an example of how far the expert can move and the corresponding tactile sensor reading. Here's the final performance of the policy for each method. Our method can move the farthest comparing to the other baselines. Here are the corresponding training curves. Directly applying TD3 on the offline dataset fails. The performance is even worse than behavior cloning. Both offline RL baselines, BCQ and Bear, do not perform well on this task. Our method outperforms the other baselines and achieves similar performance as the expert, despite the fact that average quality of the dataset is low due to the replay buffer. It demonstrated how our method can fully utilize the dataset. We also evaluate our method on the D4L benchmark. Here are some of the qualitative results on the locomotion tasks. Here are some of the training curves. Our method is in orange. We can achieve similar or better performance than the other baselines. More results on the D4L benchmarks, such as the hand and the kitchen environment, can be found in the paper. To further analyze the results, we took this experiment as an example and checked how accurate the Q functions are. During evaluation, we record the true return for the state action pairs and then compare them to the estimated Q value. We found that we have the lowest mean square error of Q values. Note that the MSE for Bragg is close to 0 at the beginning because the return is also close to 0. We also measured how many of the state action pairs are underestimated or overestimated. Here's a plot for the percentage of overestimated state action pairs. Both BCQ and Bayer suffer from overestimation, and Bragg suffer from underestimation. In some cases, we may allow some amount of out-of-distribution actions if we trust the extrapolation of Q functions. So we add an optional perturbation layer to our method inspired by BCQ. It is trained to add a residual on top of the latent policy output. We have a clear separation of in-distribution generalization by the latent policy and out-of-distribution generalization by the perturbation layer. Since this is an optional component, so when should we use it? We train the policies with different allowed perturbation, and we found that it could be helpful when the dataset does not contain high-quality rollouts, such as the medium or the random datasets in the DFLR benchmark. And when the dataset contains high-quality rollouts, the perturbation layer is usually harmful, because in these cases, we can only use the dataset, if we can use the dataset effectively, in-distribution generalization should be enough. In summary, we propose to learn a policy in the latent action space for offline IRL problems. It naturally avoids out-of-distribution actions, and it allows the flexibility for improvement. We look forward to more deep reinforcement learning experiments on real robots with offline IRL algorithms. For more information, please visit our website, and welcome to our interactive session for more discussion. This work is supported by the following sponsors. Thank you.
Okay, thank you very much. Let me see whether I got some questions. No, not so far. I have a very quick question. So could it be the case that he's taking an action that he has seen in dataset, but not for the specific state that you are currently in, and that's for this case still out of distribution, or is that somehow prevented?
So the out of distribution action is defined by the action condition on state. So hopefully we can only select actions that is seen at the same state in the data set. However, for a continuous action space, you probably won't see exactly the same action or exactly the same state. So there's some kind of generalization happening within the data set. So it could be the actions that is generalized for a nearby state.
Okay, good. Thank you very much. So then next, we have another question. There's one question from Mariah. How do you choose the dimensionality of the latent action space?
We keep it simple and use the dimension as in previous work. So it is currently set to be twice of the original action space for the environment. But this is just to keep it the same as the previous work.
Okay, good. Thank you very much. So the next speaker is Roland Hafner from DeepMind, and he will talk about towards general and autonomous learning of core skills, a case study in locomotion. So Roland, please go ahead.
Yeah, thank you, Gerhard. Can you see my slides and hear me?
Yeah.
Cool, thank you. Hello, everybody. My name is Roland Hafner. I'm a research scientist at DeepMind, and this is the presentation of our paper towards general autonomous learning of core skills, a case study in locomotion, that contains work of all these great people that are on the slide. So first, let me start with a bit of motivation. In our group, we see our long-term research goal as solving an important subfield of AGI, which is to solve general control problems. Therefore, we work towards an artificial general control intelligence, or AGCI. For us, this becomes manifest in a single agent architecture, which progress towards AGCI can be measured by 4 main criterions, which basically also define our research agenda. So we expect it to be robust, to work out of the box without manual hyperparameter tuning, serving a broad range of tasks and a broad range of domains and domain instances. Autonomy for us means that it deals with raw inputs and actions, only learning with minimum prior knowledge without too much engineering that we have to put into the solution. Still, it should be able to learn complex real-world driven tasks and at the end of the day, understand also something about the complexity. And overall, it should be data efficient enough so that we can learn from scratch also on real hardware. We are constantly improving our methods by applying and testing them on different domains and tasks. Here we already saw very good results in different domains like manipulation from raw pixels, dynamic manipulation from raw pixels like in this bowling in cup example, or other real-world feedback control-driven tasks. And in this paper now, we summarize our first results of applying our methods to a, for us, new domain, namely locomotion, where we wanted to find new challenges and advantages. We ground our experiments on a platform that follows a modular approach in hardware, which is the Heavy Robotics DAISY platform. As it is robust enough to do learning experiments from scratch on the real hardware, provides rich sensor information, and in principle also allows to build a wide range of different robots that we could have. As it still would be very difficult to build a large set of robots in the real world, we also built a modular simulation that allows us to perform a large number of experiments on a large set of very different robots in simulation. Overall, we have a zoo of 9 different simulator platforms with very different kinematics and dynamics properties, as you can see here, ranging from 3 to 6 legs with arms or even with wheels. The main goal of this work now was to investigate how powerful our approaches can be and what we can gain with them in the domain of locomotion with respect to 3 main aspects: the autonomy, the robustness or generality, and the efficiency on this large zoo of different robots with these different locomotion properties. So first, what does autonomy mean in this context and what can we gain from it for locomotion? As we follow our basic approach of using reinforcement learning to learn from scratch or minimal prior knowledge, we already have some level of autonomy here. For example, before we start learning on a new robot, on a new platform, we don't have to collect demonstration data for this individual platform or necessarily build a simulation before we can start the experiment. To further improve autonomy for locomotion, we use 2 additional approaches. The first is that we want to base all observations and rewards only on the rich onboard sensory information of the robot. In consequence, the robot can learn without dedicated infrastructure like external mocap systems or some other sensors, in principle allowing learning anywhere, not only in dedicated lab settings. The second is that we want to use very simple reward schemes that are only based on simple kinematics relations and are the same for all robots, which means that we don't need highly human engineered shaping rewards that are specific for a certain robot platform. So this approach gives the agent and the robot a very high level of autonomy. The main question now is if we can still learn useful and interesting locomotion behaviors over the full zoo of creatures in a data efficient way, which we investigated in this paper over a set of 8 example skill rewards that follow all the same principle. So here's one of the simplest examples of such a skill, which is to lift a certain foot. The reward is a simple combination of keeping the torso leveled by using the IMU orientation estimates, keeping it still by using the gyroscopes, and lifting the foot 5 centimeters over the ground using the IMU and some referent points and forward kinematics in the feet. Using our agent that learns from scratch just by interacting with the robot, we get the expected behavior after only 60 episodes of interaction, which corresponds to roughly 20 minutes of pure interaction time. Another good example how powerful these simple rewards are is the walk forward skill. The definition of the reward is again only based on onboard sensors. And again, we want to keep the torso leveled while roughly speaking giving reward for moving some reference points defined on the robot forward relative to each other. Also, the reward is defined in a very simple way. We can learn a very good symmetric and efficient gait for the hexapod in about 60 minutes of interaction from scratch. Also, being very simple, these reward schemes are very general, which means that the same reward definition for the same agent and the same hyperparameters works over different locomotion creatures with very different kinematics and dynamics properties. Here's an example for the lift foot skill. While a human engineer would agree that we need a completely different approach for a hexapod and the 2 quadrupeds, as keeping balance for the quadrupeds is now a problem, we can learn a good behavior on all 3 creatures with the same settings. If you apply the simple reward to a biped now, we suddenly have completed a different level of complexity for the task. Suddenly the simple reward, it's the same as before, the definition of lifting a foot while keeping the torso leveled, gets to balancing on a single foot without falling. Still, the same agent with the same hyperparameters can learn it from scratch for all the bipeds. This shows an important property of our approach. Although the reward schemes are very simple, they still show a high richness and versatility of behaviors in the learned skills. Another very nice example for this is what the agent learned with the same skill rewards for the biped with arms in this example, which also looks a bit lazy, to be honest. As this task is already quite complex, we need some episodes more to learn this, but with under 6 hours of interaction for the most difficult biped, it is still quite data efficient. We get comparable results for the walk forward skill. So the same agent with the same hypers and the same reward can learn a highly symmetric and efficient gait for a 3-legged version of the daisy, as well as the hexapod and the quadrupeds from scratch. While the type of the gait that develops specializes on the specific robot and is completely different. A really exciting result for us was that these simple rewards work to get a very nice gait for the bipeds as well. Also here, the learned behavior specializes on the specific robot to optimize the gait. Again, an interesting insight is that while not taught at all, it learns to use the arms to help to balance while walking forward. Still, the learning process is pretty data efficient, as we can learn this even for the most complicated biped in under 7 hours of interaction. So overall, we do not claim at all that these skill definitions we are using in this work are all you ever need to generate sufficient locomotion behaviors under all circumstances. Rather, the main idea of this work was to investigate how far we can get with a simple set of skills we defined. And we were really surprised how far we were able to go in 2 ablations we made. What we found is that all creatures were able to overcome obstacles up to a height of several centimeters just using the simple walk forward reward, as you can see in these examples. Especially the daisy hexapod seems to be even more robust in this sense, as it is able to overcome obstacles up to 20 to 30 centimeters. Also, if you put passive skates under the feet, using the very same reward schemes as before, we get a completely different locomotion behavior. Again, it also shows a high level of creativity how the feet and the arms can be used to locomote now, without being anything about the arms in any reward definition. As we saw up to now, using a powerful offline reinforcement learning algorithm, these simple rewards can generate very versatile, diverse locomotion behaviors of a large set of different robots just learning from scratch. The last step is now to build a versatile locomotion module that learns more than just a single locomotion skill. To achieve that, we build upon the same basic idea we published in the domain of manipulation in the Simple Sensor Intentions paper. There we showed that using the simple and versatile reward definition, comparable to what we found here, in combination with a multitask reinforcement learning approach like scaled auxiliary control, where we execute multiple tasks and run multiple tasks in parallel, is a powerful method to solve complex tasks without too much human engineering in a very data efficient way. If we use this approach to learn a versatile locomotion module now, we see 2 main advantages. The first big advantage, as this locomotion module learns a set of core skills in parallel, following the scattered auxiliary control principle, we do not only learn to solve the skills from an initial set of starting states, but rather learn the transition between all of the skills. In consequence, we learn even more versatile and robust skills that in this example not only learn to walk forward and backward, but also to switch between them without falling, as you can see here for the biped. One of our main goals can be seen in the second example. In addition to the basic core skills, we add a very sparse and difficult task, in this example, a reach target skill to the locomotion module. While the baseline of just learning the sparse task from scratch fails, we can learn all skills in parallel from scratch in our locomotion module, finally solving difficult sparse tasks in a couple of hours. And as an additional advantage that comes with this approach, we can also increase the general data efficiency for learning all skills. For example, for the bipeds, we can save up to 8 hours of interaction time for learning stand, walk forward, walk backward in parallel, compared to learning them one after another. Finally, we showed that we can reproduce the most important walking experiments from simulation on the real daisy quadruped. The quadruped is what we get when we remove 2 legs from the original daisy hexapod, and that was that's a system that's not shown often in literature before. Here is an example of training the walk-forward core skill from scratch using the same agent, the same hyperparameters and reward scheme we used in simulation. It starts from scratch. After 10 episodes, it tries to make roughly a step and still explores, and from episode 40 to 120, develops a pretty good gait in a very comparable way it does in simulation. This means that we can learn a gait in only 40 minutes of interaction, while the experiment runs for about 2 hours. Also, if we apply the multitask setting, we see overall a pretty good alignment with the results from simulation. In this example, we can learn 6 core skills, which are lift each of the legs, already 4, walk forward and walk backward in parallel. In general, as these real-world experiments on the quadruped daisy align pretty nicely, we have good hopes that the other results from simulation we showed are also somewhat meaningful for the real world. So to conclude, in this work, our main goal was to show in form of a case study that we can build a versatile and robust locomotion module using our up-to-date off-policy reinforcement learning methods. We showed that the basic approach is robust and it works over multiple domains on multiple very different platforms in locomotion with the same hyperparameters. The very simple reward schemes showed that we can reach a very high level of generality and learn very interesting and useful locomotion skills over a set of 9 different simulated and 1 real robot without human engineering effort that we have to spend on the single platforms. Yet the level of autonomy that we can reach is pretty high, as the agent only uses onboard sensors, so it can learn without external infrastructure in principle. Especially by using a multitask reinforcement learning approach, we can learn for all the platforms a versatile locomotion module in a very data efficient way that is able to solve complex tasks and learns to walk on a real quadruped robot in only 40 minutes of interaction. An interesting fact, for example, is also that the very same hyperparameters and basic methods also work for other domains like manipulation. But most important for us, we showed that building this versatile locomotion model is possible, which is for us just another very small step towards this AGCI. Thank you very much.
Yeah, thank you very much, Roland. We have time for one quick question. So no question from the Q&A. So I would have a quick one. So for switching between the skills, so how do you do it? Do you do it randomly, or is it also learned when to switch?
So in the scattered auxiliary control, we have 2 methods. We have the SAC-Q and SAC-random. For the just learning all parallel skills in all auxiliary skills in parallel, we use the random switching. And for this reach task we saw, we use the Q scheduler, and that is a learned schedule, an optimizing schedule.
Okay. There is another question, but I don't think we have time, so maybe that can be done then offline. So you can see it in the Q&A and you can answer it for that. Okay. So yeah, thank you very much. Our next speaker is Carl Birch from the University of Southern California, and he will present his work with co-authors on accelerating reinforcement learning with learned skill priors. So Carl, please go ahead.
I think Roland is still sharing his screen.
Yeah, Roland, you have to stop sharing your screen.
How do I do it? Sorry.
Okay.
Okay. Can you see my screen now?
Yeah.
Okay, great. Hello, everyone. My name is Carl Birch, and today I'll be presenting joint work with Young-Woon Lee and Joseph Lim. To get an intuition for our method, let's look at a task that we're often performing in our everyday lives, which is the task of indoor navigation. And when navigating a new indoor environment, we're actually leveraging a lot of previously learned skills, like entering buildings, making turns, traversing hallways, or climbing upstairs. In fact, we have learned so many of these skills before that it's infeasible to explore all of them when faced with a new navigation task. So instead, we actually have a very good prior or intuition over which of these skills make sense to explore when given a certain situation, like here, where it's very natural for us to, for example, go straight or turn left, but it's also very natural not to turn right and run straight into the wall. So where does this intuition come from? Effectively, we're leveraging a lot of prior experience that we've collected over the course of our lifetime in order to learn 2 key things. On the one hand, we're learning the skills themselves. We're learning how to go through a hallway or turn around the corner. But then we're also learning this prior that tells us, given the current situation, which is a set of meaningful skills that we really should explore here based on what skills we explored in similar situations before. And this is what allows us to take this very large set of skills that we have learned all together and narrow it down to a much smaller set of skills that are meaningful to explore, and therefore learn downstream tasks much more efficiently. And this is not only true for navigation settings, so we can observe similar things in manipulation, where we have lots of experience manipulating different objects that helps us to learn how to manipulate new objects. Or also in kitchen environments, where we have interacted with many different kitchens before, and therefore have a good idea of how to efficiently explore a new kitchen environment. Now, in our approach, we're trying to take a very similar intuition, and we assume access to a very large data set of pre-collected robot experience, of that robot solving many different tasks, but not the one that we're currently trying to learn. And then from this data set, we can extract two things. On the one hand, we can extract a set of reusable skills. And now the larger the data set we're learning from is, the more of these skills we will actually be able to extract. And so in order to efficiently explore them, we also propose to learn this skill prior that tells us, given the current state, what are the skills that I should explore, and maybe also what are the skills that I should better not explore. And we can take these two things together and propose a scalable RL algorithm to efficiently learn how to solve new downstream tasks. Now, before we go into the details of our approach, let's try to get a better intuition of what kind of prior we're trying to learn. And we will use this example of an intersection navigation task to illustrate this. And on the right side, we're visualizing all the driving skills that we have ever learned over the course of our lifetime as this gray circle. And now if you're in a situation like this, there are a bunch of skills that make sense to explore, like, for example, taking a left turn or turning into any of the other streets that are available. But then there's also a lot of skills that you really don't want to explore, like, for example, backing up into the car behind you or driving off the road somewhere. And so our goal here is to learn a distribution that only captures those skills that are good to explore and excludes all the other many skills that I have learned before, but that don't fit the current situation. And when we have learned this distribution, we can leverage it for more efficient exploration on any downstream task. So how can we learn this distribution? We will start by sampling trajectories from our offline data set. And we will crop out random subtrajectories of a fixed length h that come with actions. And this action trajectory is what we will call a skill. And then we learn a model that looks very much like an autoencoder. So it takes that action trajectory, it embeds it into a low-dimensional skill space, and then decodes the original action trajectory. And we apply a regularization loss in that skill space towards a fixed prior distribution, similar to a VAE. And this is what allows us to learn like a more smooth representation of these skills. And now what this encoder output represents is really the current skill that we're currently encoding. But then crucially in our project, we also try to learn this skill prior network that takes in the current state and outputs this prior distribution that captures all the other skills that are also meaningful to explore in the given state and excludes any other skill that we have previously learned, but that does not fit the current situation. And we can learn this distribution simply by regressing the output of our skill prior onto the output of our skill encoder network. And once we have learned both the skills and the skill prior, we can leverage them for a more efficient downstream RL by leveraging a hierarchical policy learning scheme. So here we learn a skill policy that outputs latent skill embeddings Z instead of primitive actions, and those can be decoded into executable actions using the pre-trained skill decoder. Now, crucially, we also want to leverage our pre-trained skill prior to regularize the output of our skill policy during training, such that it only is encouraged to explore those skills that are meaningful. And in order to understand how that exactly works, we need to look at a concept that's very common in RL, which is called maximum entropy RL. And in maximum entropy RL, we are taking the usual maximum reward objective in RL, and we're adding another term that tries to encourage the policy to maximize its entropy. So that means it should act as randomly as possible while still trying to solve the task. And we can rewrite that second term equivalently as a KL divergence between the output distribution of our policy and a uniform prior over actions. So if you were to display this in the 1D example, it means that you're encouraging your policy to really explore all the actions that are available with equal probability. Now, what that means if we learn a policy over skills instead of primitive actions is that we encourage our policy to explore all the different skills that we have ever learned with equal probability, which is not desirable because there are probably many that don't make sense to explore in the current situation or are even dangerous. So in our approach, we instead propose to regularize our policy towards this learned skill prior that is non-uniform and encourages more efficient exploration. So you can see here that by minimizing this KL divergence, we're really encouraging our policy to explore those skills that are meaningful and discourage it to explore the other skills that we really don't want it to explore. And we call this approach skill prior RL or spiral. In order to optimize this objective, we can actually leverage a lot of existing algorithms that try to optimize this maximum entropy RL objective, most famously maybe the soft actor critic algorithm, which is a current state-of-the-art algorithm for off-policy RL. And you don't really need to understand all the details on this slide, but what is important to note is that we only need to modify this algorithm in a few key places in order to optimize our skill prior regularized RL objective. So once you start from one of the many SAC implementations that are out there, it's actually very easy to implement our algorithm. Okay, to sum up what we've learned so far, basically our approach can be summarized in two stages. So in the first phase, we're learning how to extract skills from a large offline data set. And then in the second stage, we use it for downstream RL using the skill prior regularized formulation we just talked about. Okay, we're evaluating our approach, Spiral, on 3 different environments. In each of them, we assume access to a large data set of offline robot experience that we have collected. And we want to test transfer of these skills and skill priors onto new target tasks that have not been seen during training and are usually requiring the agent to learn longer horizon tasks than that we have seen during training time. And let's first look at what kind of priors we're aiming to learn. And we will start with this maze navigation example, where we have a training data set of randomly sampled mazes, and the agent tries to reach a goal in these mazes. And the kind of prior that we're hoping to learn is similar to what we've seen before. So we hope that our agent can kind of learn to navigate the hallways and to get through these narrow doorways while avoiding to collide with any of the walls. And if we look at what kind of prior this agent actually learns, we can compare 2 cases. So on the left side, we compare what happens when we randomly sample the set of learned skills. And you can see that it ends up with an agent that actually often collides with the walls and struggles to get out of these narrow doorways. On the other hand, if we sample from that learned skill prior we talked about earlier, we can see that the agent indeed avoids collision with all the walls and is even able to navigate these long, narrow hallways. So it's much more efficient at exploring this maze environment. And we can also observe that if we roll out these trajectories for longer, so here you can see that our approach Spiral is able to very widely explore this maze environment because of the learned skill prior, whereas alternatives that try to use a uniform prior over skills, so not the learned skill prior, or try to learn a prior over primitive actions instead of temporally extended skills, struggle to explore this maze as widely and therefore also struggle to learn downstream tasks. Similar observations can be made on the block stacking environment, where we have lots of data of the agent stacking different blocks in random locations. And if you look at the kind of skills that we learn and the prior that we learn, you can really see that it encourages targeted exploration towards areas where the agent can really learn how to pick up blocks and solve new downstream tasks, which can greatly improve the efficiency on downstream task learning. Finally, we're evaluating our approach on a kitchen manipulation environment, which is taken from a paper by Abhishek Gupta et al. And in this environment, we actually have access to a large data set of human teleoperated data of the robot interacting with many different parts of this kitchen environment. And our hope is to learn a new new manipulation task in this kitchen environment. And now we can attempt to solve this with normal soft actor critic without using any of the available data. And you can see that this really struggles to solve these long horizon sparse reward tasks. We can also look at the baselines that we talked about before that try to use skills without a learned skill prior or try to learn priors over primitive actions. And you can see that they kind of learn to solve some of the subtasks because they have access to this prior data. However, they struggle with the very long horizon tasks. And in contrast, our approach Spiral is able to leverage both the learned skill embeddings and the skill priors to solve these long horizon complex manipulation tasks efficiently. We also observe that when we look at the quantitative results, and here our approach outperforms not only the baselines we just talked about, but for example, also baselines that try to initialize a soft actor critic learning with a behavioral cloning policy. Finally, we want to highlight some of the beneficial aspects of our approach. On the one hand, because we have this 2-stage procedure where we first learn the skills and then learn to solve downstream tasks, we can actually leverage the same set of skills and skill priors to solve many different downstream tasks. And we demonstrate this here in the maze, where we can leverage the same skills to solve multiple, or to learn how to navigate to multiple target goals in the maze environment, which is great because it means you only need to do this costly step of pre-training the skills once and then can really focus on solving downstream tasks. And finally, we wanted to investigate how robust our approach is to suboptimal training data. In order to do that, we trained a behavioral cloning policy on this expert-like data and collected data from this behavioral cloning policy, which is substantially suboptimal because of the accumulating errors. However, when we train from this data, we can still see that our approach is able to learn how to solve these long horizon navigation tasks, which we attribute to the fact that while the data is globally very suboptimal, on a local scale, it can still tell you how to navigate around the door, around the corners, get through the doorways or avoid collisions. And this is what our approach can leverage to still solve these long horizon tasks. And that's great because if you think of data collection at a large scale, it's really a much more meaningful assumption that you can handle some suboptimality in your data than if you were to require that all of your trajectories are optimal. Okay, to sum this up, in our project, we show how we can use learned skill priors to accelerate downstream task learning. We propose Spiral, which shows how to extract skills and skill priors from large unstructured data sets. We show how we can use learned skill priors to enable efficient exploration even when we have learned a lot of skills. And we can show that Spiral can learn complex and long horizon tasks on which conventional RL algorithms struggle. Now, thanks for your attention. If you have any questions, I'm happy to take them now. Come to our interactive session or check out our website also if you want to have a look at the code. Thanks a lot.
Thank you very much. We do have a couple of questions. So the first one is, the skills you extract are not conditional on the current state. Would you see a way where a skill would be more general? For example, reach the cattle, but a cattle could be in many different locations. Yeah, so this is a great question. I think we have tried this. We have actually some experiments in the paper, in the appendix, that try to condition the low-level skill on the state. And we did find that this can make the learning of the downstream task more challenging. One reason could be that if you condition the low-level decoder on the state, it means that the dynamics of how your policy output action translates into actually executed actions changes depending on which state you're currently in, which does seem like it would make the policy learning harder for the high-level policy, because now the same output can reach to very different outcomes depending on what state you're in. So that could make the dynamics just a little bit more challenging. Okay. And another question is, the learned skill prior to restrict the search space is a cool idea, but the potential cost is that it may hamper exploration, i.e. maybe it's worthwhile trying a skill on a new task that you wouldn't otherwise use. How do you balance this? So that's totally a valid concern. So the skill prior mostly helps if it's well aligned with the kind of downstream task you're trying to solve. Now, our constraint is somewhat soft. So there's this weighting term that weights between maximizing reward and minimizing the divergence from the prior. So the policy definitely has the choice to violate that constraint if it really helps with solving the task. And this trade-off is something that you can tune. There's actually a way of automatically tuning it, but you still need to choose one hyperparameter. And I'm happy to discuss this more in detail later. We also do have some experiments where we test what happens if you add a lot of random data to your prior training data set, which really means you're kind of imposing a very non-optimal prior onto your downstream learner, because you have a prior that tells you to randomly try everything. And we can see that this really impairs the performance on the downstream task. So definitely you would need to have a training data set that is somewhat aligned with what kind of downstream tasks you're interested in. But as long as the training data solves meaningful tasks, that's kind of an assumption that might be reasonable. Okay, good. Thank you very much. For the sake of time, I think we have to take the remaining questions offline. Thank you very much, Carl. So the next speaker is another Carl, so Carl Smackpepper from the University of Pennsylvania. And he will talk about reinforcement learning with videos, combining offline observations and interaction. So Carl, please go ahead.
Okay, hello, I'm the other Carl, and I'll be talking about reinforcement learning with videos, combining offline observation with interaction. Reinforcement learning from scratch is difficult, requiring large numbers of samples to accomplish even simple tasks. Collecting example trajectories through teleoperation can speed up learning, but gathering these trajectories is expensive and time-consuming. An alternative approach would be to use observations of humans, as videos of people are an easily accessible source of data. We therefore ask the question of how can we leverage observations of competent human behaviors in order to improve the performance of robots. Many approaches have attempted to perform imitation learning on observational data by attempting to learn a policy that can match the observed state transitions as well as possible, or by attempting to use the observed data to learn a reward function, which can be used for reinforcement learning. However, both methods of imitation learning are limited because they assume that the observed trajectories are optimal. In comparison, our approach is able to improve upon the observed trajectories by gathering interaction data. Existing methods attempt to integrate demonstrations into reinforcement learning algorithms, but these methods rely on kinesthetic or teleoperated demonstrations, and therefore require actions and other information that is not available with observational data, especially that of humans. Our approach is able to work directly with human data. Model-based approaches have also been proposed to leverage observational data, including in our prior work. In contrast, we now show that observational data of humans can be used in standard model-free reinforcement learning pipelines. Finally, we draw similarities to several works that have tackled domain shift between observation and interaction data, using techniques including domain confusion to learn invariant features, or by synthesizing images in the target domain. We most closely follow the approach of learning invariant features to aid domain adaptation. Our general approach is to put both the human observation data and the robot interaction data into a replay pool, and then run a conventional batch reinforcement learning algorithm on it. This approach is appealing because of its simplicity, allowing to leverage existing RL and exploit feature advances in the field. However, it presents three main challenges. Offline video has no actions, no rewards, and can exhibit substantial domain shift in comparison to the interaction data. We show that simple approaches can solve all three of these challenges. In order to solve this problem, we label the last state of each observed trajectory with a large reward, train an inverse model to predict actions, and use adversarial domain adaptation and paired data to handle domain shift. I'll now talk in detail about each of these three components. We take close to the simplest possible approach to reward prediction. We predict the reward of any next state pair to be a constant small value if the state is not terminal, and a constant large value if the state is terminal. These constants can usually be read off of the environment. We use these predicted rewards to label the observation data, which naturally lacks rewards. Even when all of the observed trajectories are successful and the ground truth reward is sparse, this method may predict somewhat incorrect rewards, as the agent may reach the goal state before the end of the episode, causing it to label successful states with small rewards. Despite the naivety of this approach, it performs remarkably well in a variety of environments and with different qualities of observation data. In order to get the actions, we train an inverse model on the interaction data and use it to predict actions for the observation data. This simple approach to learn from action-free observation data has also been successfully used in our prior work, learning predictive models from observation and interaction. In order to overcome the domain shift, our inverse model and the reinforcement learning algorithm operate on domain invariant encoding H rather than on the raw observations. We learn this domain invariant embedding using adversarial domain adaptation. We additionally find that incorporating a small amount of paired data significantly improves the quality of the learned embeddings. For each pair of paired data, we minimize the mean squared error of their embedding. Taken together, we present reinforcement learning with videos, or RLV, by using simple approaches of assuming the terminal state is high reward, of learning an inverse model on the interaction data, and learning a domain invariant embedding. We can gather all the information needed to feed the observational data into a standard batch reinforcement learning algorithm. We construct a batch made up of samples from the interaction data using the learned embedding H and the true actions and rewards. We combine the samples from the interaction data with samples from the observation data, which are augmented with the prediction actions and predicted rewards. We then train the reinforcement learning algorithm on the resulting combined batch. Our approaches to synthesizing the actions and the rewards for the observational data are simple. We ensure that they are sufficient to allow simulated robotic agents to learn from observing humans. Now we'll discuss our experiments. We design our experiments to answer three main questions. First, despite the assumptions our reward labeling makes, is RLV robust to unsuccessful or suboptimal observations? Second, can RLV leverage observational data to help it solve difficult robotic tasks? And third, can RLV use human observational data to solve these tasks, despite the visual and physical domain shift between humans and robots? First, we examine the effects of different qualities of observations in a simple acrobat environment, where an agent must swing up a double pendulum. We train an RL agent on the acrobat task and gather observations from it at different points in training, giving us simulated sets of observations with different success rates and achieved rewards. We show the achieved reward versus the number of environment steps for 3 different qualities of observations. We first consider the case where the observed trajectories are near optimal. In all charts, the dashed line shows the true rewards of the observed trajectories. Both our method, shown in orange, and existing methods of learning from observations, behavior cloning from observation, or BCO in red, and imitating latent policies from observation, or ILPO, shown in blue, are able to learn with many fewer samples than standard reinforcement learning, which is shown in green. Gathering near-optimal data is easy with simulated data, but almost impossible with humans, as the optimal policy for a human is often different from the optimal policy for a robot due to the differences in their morphologies. We next consider the case of where the observed policy is close to random. Our approach, in orange, is able to leverage even the near-random observations to initially learn faster than standard reinforcement learning, while the other methods of learning from observation, BCO and ILPO, attempt to mimic the random policy. Unfortunately, our method converges to a suboptimal policy when given the near-random observations, as the reward generation for the observed trajectories assumes that the terminal state in each trajectory is successful. Fortunately, the human observations that we want to use are not random. Instead, the human is clearly executing a desired task, but doing so in a way that's slightly different from how a robot would best perform it. Therefore, we consider the case where the observed policy is better than random, but still clearly suboptimal. In this case, our approach is able to learn much quicker with many fewer samples than standard RL, while at the same time converging to the optimal reward. After showing that our method is robust to different qualities of observations, we next need to show that it is able to scale to more complicated and realistic robotic tasks. Therefore, we evaluate our performance on simulated robotic tasks in the Mijoku simulation, namely pushing and door opening from state and visual observations. These tasks are challenging as the robot only receives a sparse binary reward, and in the case of the visual door opening and visual pusher tasks, only receives raw pixel observations. We once again gather observations by fully training the standard reinforcement learning method to solve the task, and then observing the resulting policy. Our approach, in orange, is able to significantly reduce the number of samples required to learn these tasks in comparison to standard reinforcement learning approaches in green. Existing methods of learning from observations were only tested in the state pusher environment, as they fail to perform well in these much more complicated environments. Finally, we consider 2 tasks using human data, pushing an object and opening a drawer. Unlike the simulated experiments, which only allowed us to study the inverse model and the reward prediction components of RLV, both of the tasks using human data exhibit substantial domain shift, visually, in the morphology of the agent, and the dynamics of the environment. We used 300 frames of paired data in the pushing domain and 500 frames in the drawer opening domain to aid domain adaptation. The robot data in all the pairs are taken from random robot exploration and automatically matched to human observations. Therefore, there are no paired frames where the robotic agent has successfully completed the task. Our approach is robust to imperfect pairing between the domains, such as the numerous times where the human hand is in contact with the puck, while the robot arm is not. Despite these differences in pairs, causing noticeable differences in the dynamics of the environment at that state, reinforcement learning from videos is still able to leverage the human demonstrations. We show RLV in orange demonstrates improved performance over standard reinforcement learning in green, requiring half as many samples to achieve the same level of performance due to RLV's ability to exploit the human data it was provided with. We also show better improvement than reinforcement learning augmented with R&D, the state-of-the-art exploration bonus, shown in blue, showing that our approach does more than simply encourage exploration. We present reinforcement learning with videos, an approach to leverage observational data of humans or other dissimilar agents to reduce the number of samples an agent requires to learn a policy. The paper, as well as code and data, are available on our website. We will also be at the first interactive session today, so please stop by. Thank you. Are there any questions?
Yeah, thank you very much. Let me see whether we have right now some questions. No, but maybe some more will be coming in. Since I have a question. I mean, so you basically said that you just use this notion of a terminal state as a reward, yeah?
Mm-hmm.
Have you thought about using some inverse reinforcement learning techniques to obtain the reward, maybe a little bit more accurately in that case?
Yeah, so we did some experiments over how much the impact of having a very accurate reward function matters. And we find that having better rewards, shown in the blue line where we had access to oracle rewards, offers some improvement. But we found that the largest quantities of improvements were from improvements in the domain adaptation. So I think that doing something more sophisticated with the rewards would be helpful and could potentially improve performance by a factor. But we focused most of our time on getting the domain shift working so we could actually leverage human data.
Okay, thank you very much. Okay, so we still don't have questions on the Q&A. Oh, no, there's one. Okay. So for the human data, how accurate are the learned actions with respect to the Baird robot data? How well does the model handle the domain shift? Does it need to be very accurate for the model to do well?
Yeah, so how accurate are the actions? We didn't run experiments for that in this paper. In our previous paper, we also ran an inverse model on human data and found that it was able to get pretty decent action representations. So if your hand moved in a direction, the direction it thought the hand would move in would be plus or minus, I don't know, 5 or so degrees. So the actions are decently accurate. I don't think I remember the rest of the, okay. How well does the model handle domain shift? There's still a very noticeable difference in performance between the performance with human data and performance with simulated robotic data. So I would still say that while we handle domain shift adequately, there's definitely room for improvement there. And if the we also have some experiments with when we don't have pair data, so when our domain shift fails, and it achieves somewhat similar performance to using an exploration bonus when our method with failed domain shift. So we think that potentially when the domain shift fails, we're basically telling the model there's a bunch of states that are someplace that's unreachable because there's no nice mapping between human and robot states, and that those states have high reward, which makes it so our approach with failed domain shift somewhat degenerates into being an exploration bonus.
Okay, thank you very much for that. I think the remaining questions we have to take offline for the sake of time. So that already concludes the 5th session, the reinforcement learning session. Thanks everybody for attending. We have now 15 minutes break, and then I think we continue with the tutorial from